Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Deep beneath the crust of our planet lies a mystery that has eluded explorers and geologists for centuries. We often think of Earth's water as a visible resource, vast oceans, winding rivers, and sprawling lakes. However, the majority of the world's accessible fresh water isn't on the surface at all. It is tucked away in the silent, dark pores of underground rock layers known as aquifers. For a long time, mapping these hidden reservoirs was an exercise in guesswork, involving localized well measurements that barely scratched the surface of the global picture. But everything changed when we stopped looking down and started looking from the heavens. This is the story of the Gravimetric Ghost, a scientific phenomenon where the subtle dance of satellites in orbit allows us to weigh the water hidden deep underground. To understand how we can see water from space, we first have to rethink our concept of gravity. On a standard classroom globe, gravity is often treated as a constant, uniform force pulling everything toward the center with the same strength. In reality, Earth is a lumpy, uneven mass of varying densities. Mountains, deep ocean trenches, and thick tectonic plates create a gravitational field that is ripple-like and inconsistent. When a satellite orbits Earth, it doesn't move in a perfect, smooth circle. Instead, it experiences tiny tugs and pulls. If it passes over a heavy mountain range, it speeds up slightly as the extra mass pulls it forward. If it passes over a hollowed-out basin, it slows down. This sensitivity to mass is the key to our cosmic scale. In 2002, NASA and the German Aerospace Center launched a revolutionary mission called GRACE, the Gravity Recovery and Climate Experiment. GRACE consisted of two identical satellites orbiting Earth, one following the other at a distance of about 220 kilometers. Scientists affectionately nicknamed them Tom and Jerry because they were constantly chasing each other. The magic happens in the gap between them. Using microwave-ranging instruments, the satellites could measure the distance between themselves with a precision thinner than a human hair. This incredible accuracy allows them to detect the smallest changes in the Earth's gravitational pull below them. As the lead satellite approached an area with higher mass, like a massive underground aquifer, the increased gravitational pull would tug it forward, momentarily increasing the distance between the two crafts. Then, as the trailing satellite reached the same spot, it too would be pulled, closing the gap. By tracking these microscopic fluctuations in orbital distance, scientists could create a map of Earth's gravitational anomalies. But here is where the ghost comes in. While mountains and rock formations remain relatively static over human timescales, water is dynamic. It moves, it evaporates, it falls as rain, and it is pumped out by humans for agriculture and industry. By comparing gravity maps from month to month, the static, background, gravity of the rocks cancels out, leaving behind a shifting signal, a gravimetric ghost. This ghost represents the change in mass caused almost entirely by the movement of water. Because water is heavy, its depletion or accumulation changes the planet's local gravity just enough for Tom and Jerry to feel it. This technology revealed a sobering reality that was previously invisible. In places like the North China Plain, the Middle East, and California's Central Valley, the gravimetric ghost showed a massive, invisible disappearance of mass. We weren't just losing water, we were losing so much of it that the gravitational pull of those regions was physically weakening. These lost subterranean oceans, some of which took thousands of years to accumulate, were being emptied faster than nature could ever hope to refill them. This data provided the first hard evidence of how human consumption is literally altering the physical properties of the planet. The implications of mapping these lost waters are profound for our survival. We are now able to see hidden droughts before they manifest as dried up riverbeds on the surface. We can monitor the melting of polar ice sheets not just by looking at their surface area, but by weighing the actual mass of the ice lost to the sea. The Gravimetric Ghost gives us a scale that can weigh the entire planet's water supply from hundreds of miles up in the vacuum of space, providing a level of oversight that ground-based sensors could never achieve. However, the science doesn't stop at just identifying loss. It allows for a new kind of global diplomacy and resource management. For the first time in history, we have an objective, unhackable ledger of how much water a nation has stored underground. It removes the veil of secrecy over natural resources, forcing a global conversation about sustainability and shared responsibility. As we face a future defined by climate instability, these orbital fluctuations are our most honest witnesses to the state of our planet's health. The Gravimetric Ghost reminds us that in science, sometimes the most important things are the ones we cannot see with our eyes, but can only feel through the subtle rhythms of the universe. We are living in an era where the very motion of our satellites is dictated by the thirst of our cities and the health of our soil. For more incredible facts like this, don't forget to subscribe and turn on notifications.